very short presentation of a lot of work. So I just will try to introduce you what is Moschovakis type theory of algorithms. And I'll just have the time to give you the syntax. And maybe at one point I'll tell something that I think has direct connection with what Maria presented. So now I go quickly through the history of Moschovakis' formal languages of algorithms. So he started in 80s, 89. He introduced the formal languages of full recursion without any types, untyped version. And at that time, I was working on mathematics of so-called situation theory, which is a theory of today. I know that it was dependent types, but at that time I didn't know the word dependent because I defined everything recursively, and recursion is about dependencies. So I defined a higher order type theory of situated information. So the types there are lambda abstracts over propositions, complex relations are abstracts over something that informational pieces that look like predicate formulae. So we were working simultaneously, but I somehow didn't pay attention what he was doing at that time. It didn't occur to me to pay attention. I paid attention much later. In 2006, he probably got very irritated by me, not paying attention what he did. And he published a wonderful paper he introduced the type theory of acyclic recursion, which is simply typed theory, and I'll introduce it in the next stages. And here is the picture. So LAR and LR are two versions. The first one, LAR, this is the more difficult one, and I focus on it because it comes with a criteria for acyclic algorithms, which means that algorithms that are guaranteed to close off, to end. Well, the full recursion can go forever here and there. So, and I'll show how exactly one distinguishes between the two. So there is a denotation. So there is a syntax, formal syntax of recursion. I'll show what it is. And the terms, they define the notational semantics by induction on the term structure. The formation rules, they just like in lambda calculus. But here, the new thing is that there is an intermediate level of algorithmic semantics, and I will just briefly say what it is, but next week I'll try to give more details about it. So there is an algorithmic semantics, and the algorithmic semantics determines for each meaningful, algorithmically meaningful term, how the denotation is computed. And in all cases, even with myself, when I started in 89, 91, defended my dissertation, I applied it for semantics of natural language. And in 2006, Moschovakis, he introduced the theory again, demonstrating everything with examples for computational semantics of natural language. And natural language has direct connection to the proofs, the verification system, proof verset, for translating the natural language of mathematical texts into formal languages of provers and verifiers. Of course, here the task is much bigger because the mathematical texts, they have definitions, they have theorems, meta-theorems, etc. And there are also proofs expressed in natural language that should be translated into a formal or specification language of one or another prover and to be checked. That's the dream. So this is the big story. And now I go to the syntax. So the type system is very simple, but very powerful in the same time. So actually E is the type of the entities of any domain of objects. T is bool, for truth values, true and false. But also there is another value here that you set the star for error. So then this uses the coding. The multi-argument functions, they are coded by unary functions, and the relations are also coded by their characteristic functions. And then here curry, it's a curry system. So the blue thing there is a wonderful thing. It was introduced by Galli, and before that, it was introduced by Montague. Montague introduced in the 70s, just before died. For a couple of years, he published a significant work, especially the one that is very important is proper treatment of quantifiers of natural language. So next week, probably I'll mention here and there about him. So he didn't treat as corresponds to a possible world in Montague, intentional logic, and in Galli. But here in computer science and in provers, actually this can be the state of the memory of the computer. What is stored in memory variables in the memory of the computer, etc., etc. In natural language, this can be encoding an agent, artificial intelligence, an agent, and how this agent interprets some vocabulary, some words, and then the verbal phrases, the noun phrases, and the sentences, and how that get translated into formal language of logic. So S is very important. Montague didn't care to introduce it as a type, separate type, but he used it in the functional tau to tau. He used it there to say that from one possible world, you get this value. In another possible world, you get that value. And then he used model logic with model operators. And then if you don't have this S as a type, model operators, they're hiding quantifiers over states and over possible worlds. As soon as Galen introduced that, one will have the possibility to quantify over possible worlds inside of the terms. So exists W such that P is true in W, and W is of type S, a possible state or a possible world. And that was the major idea also in situation theory, that there it's much more complicated. Each situation is a collection of things that look like propositions. So now, here, all the time, it's a very useful tool. Moschovakis, he introduced this abbreviation for state-dependent objects of type sigma. So if sigma is a type, we have a type from S to sigma, which means that this is a state-dependent term that depends, the value depends on the possible interpretation, on the possibility in the what is the state of the machinery. And E is for state-dependent entities. Well, in the natural language, Peter, who is Peter depends on, and the agent, some smart robot, who is the robot called Peter, it depends on the situation, on the state, etc. Truth values. T corresponds to bool. So in high order logic, intentional logic for natural language, propositions are functions from possible worlds to truth values. These are the propositions. State dependent, because this is about the intentionality of the language. And this is very important in the provers and in the mathematical text. When we say theorem states this and this and this is indirect statement. And what is inside of this indirect statement depends on the mathematician who writes there. So there is certain things can be calculated outside of the theorem, other things that are included inside of the theorem. So certain things are references by the theorem, and certain things are references by the person, the mathematician who describes a theorem. So this is very important, these state-dependent truth values. And T is, if it's not state-dependent, that it's a so numbers, Moschovakis claims that pure mathematics, numbers, etc., they don't depend on states, but I'll show you example. Well, it depends. Natural language of mathematics, the texts are ambiguous, not less than the natural language of every day is much more ambiguous, but mathematical texts are also ambiguous. And everything is the context, in the context of a discourse, what the mathematician writes, and it depends. So I'll show you example. So now, the vocabulary of this theory is very important. Everything is typed. We have constants. Moschovakis, he chose in his paper 2006 finite number of constants with questions about the decidability when two terms are representing one and the same algorithm. But I just left them infinite remaining. So, and I'll jump around the conjunction, disjunction, and negation, and I'll tell another very important thing about the algorithms. There are two kinds of variables. The pure variables are the ones that we use for lambda abstractions and for the existential, universal, for the quantifiers in mathematics. And for free variables, of course. Recursion variables, these are variables that designate memory in a computing system. And this is the first thing that has ever been formalized by Moschovakis. I mix them in my dissertation. Mathematicians, we all the time mix them, use one and the same X for both, for the memory and for doing things with algebraic expression. Here they have to be kept separately. So in all of them, they are, of course, typed. So conjunction, disjunction, implication, I introduce all of the logical constants. So here the useful thing is, but one can use them in Tarskian. They can be introduced in Tarskian style, and then one has to express the truth conditions in the Starsky way. Here it's very useful to treat them just like a special constants, but special constants, because then the reduction calculus is expressed much more effectively. And here the new thing is that certain logical operators, they are state dependent. So there are two kinds of formulae that are state dependent and that are state independent. And actually I even can mix them up. And if in a formula that looks like a quantified or just even propositional formula, if there is at least one sub-formula that is state dependent, then the entire formula has to be state dependent. So this is the vocabulary. So now is we go to the this is, I try to put everything together in one slide. So the first line, 3A, this is standard lambda calculus. Which one do you like? You take it. There is variables, constants, application term, and lambda abstraction term. And the type system follows well typed. It follows the syntax of lambda calculus. The new thing is 3B. This is the wonderful thing. And here, Maria, I think at certain point, because you gave a very nice talk, I'll say how the indices are important. So here, this term looks like let expressions, right? Let P, 1, B, A1, etc. But I have proven in a paper recently, it's more than let expression. So denotationally, indeed, they correspond to Dana Scott and Plotkin let expressions, but algorithmically this is much more expressible. So then are the logical formulae and the negation. So the pure quantifiers. Why I call them pure quantifiers? Because in natural language, the two popular quantifiers in mathematics and in logical systems are exist and well. These are just two quantifiers in natural language. But in natural language, there are a lot of quantifiers, and some of them are expressible in, they can be numerical quantifiers, they can be encoded by existential and universal quantifiers, at least 3 objects, at least exactly 3, at most 3, etc., etc. With sufficient number of quantifiers that can be encoded. But there are natural language quantifiers that don't have representation in first order logic, and the most popular one is the most. At least, not at least, but a little bit, a lot, many. A lot of those Barweis prove them that they cannot be expressed in first order logic. So generalized quantifiers are popular, and Montague introduced them for natural language in his intentional logic. And there is, for certain of them, there is a, next week I'll try to present that. There is a correspondence between the generalized quantifiers and between the first order, higher order for all and exists. And there is a correspondence there. One can switch, and that's very important for the provers, because the provers, they work on, these are the major 2 quantifiers, the most important. So, but there are much more. So in natural language, the quantifiers are usually expressed by what is called determiners. And I'll show you an example with the definite descriptor, the number. So Russellian, he encoded it. There exists exactly one object, number, that has some property. But there is, here I prefer the referential. The number 3, you refer. You don't say there is exactly 1, 3 numbers or something like that. You refer to the number 3. And that's very important also for provers too. So here we skip 3G and 3H, but this is for the intentional verbs. The theorem 6 states this and this and this. And this is something that has to be scoped out. There's a lot of ambiguity there. Certain things are the speaker, the mathematician describes something. So there is no time for me to present this even next week. So here I return back after giving this syntax again. Now I return back to, so after, excuse me. So here, after I have introduced the syntax, it makes much more sense to me to tell you the difference between the notational and algorithmic semantics. The notational semantics is by the induction of all those terms. The algorithmic semantics is determined by a reduction calculus. So there is a reduction calculus introduced by Moschovakis. He introduced about 10 rules, a little bit more probably, depending the congruence relation has at least 3 rules, so one has to be quiet there, but there are 10 plus. And I have myself introduced quite many terms. Let's go back to the here. So such that corresponds to the mu operator. In the recursion theory, the mu operator is the least number that has this and this property. But that is about the number system in arithmetics and in recursion theory about numbers. Here I generalized it for much more things. Of course, we can encode everything with numbers, but better in the provers, that's very important, that mathematical text is translated not by coding, but directly from natural language of mathematician into proof terms. And such that introduces this restrictor, and it has, in certain cases, it has the Vero error. That's star that was introduced today. So now, here is the big picture. So the reduction calculus reduces every single term into its canonical form after finite number of steps. So this is effective reduction calculus. Every term, whatever it might be, can be reduced to its canonical form after finite number of steps. And the canonical form of A, if the term A is algorithmically meaningful, then the canonical form tells what is the algorithm for computing the denotation of that term. So I go back to the line 3b. So the canonical form looks for every term, looks like that, a recursive term. There is a hat term, and P1, Pn, this represent memory locations in the computer system, and the values that are the basic facts, everything decomposed into the simplest possible facts, and they are saved into the memory system. And then the value of the term A0 of the hat is computed, the rotation is computed by induction on the, so this is a system of mutually recursive equations, and this the where they look like let, but these are not let. This is a bit more. So here, there is another thing. In the let expressions, you can use with lambda term, you can encode and you can get rid of the let expressions. Here, you can't do that. So better reduction is extraordinarily important when you decide whether two terms are algorithmically equivalent, and one decides whether two algorithms are equivalent by the canonical forms to find correspondences between the recursion, between the canonical forms, so that A1 corresponds to B1, denotationally equal. So Maria, I think there, it's very important what you said there, but I didn't know to prepare such a slide. I didn't know what you are going to talk. If I knew, I would have prepared such a slide. So nevertheless, again, the algorithm for computing the denotation of A0 is actually this, in the scope. So where is a binding operator? It binds the memory location P1 to Pn by putting values into those memory locations. So this is programming language, right? So a compiler, nowadays the compilers automatically, when you have a recursive term, I'll show some examples. When you have a recursively nested term, the best way is not to use the recursive term nested one in the other, because you have to backtrack. Each sub-term has, in order to compute the value of the larger term, you start the components of the sub-terms recursively nested, and then you have to backtrack. And that's not good. Whatever the machinery powerful we have, the best way is to get iterative. And this is the iterative. If you order them appropriately, this A1 to AN, according to a ranking function. And again, I think this ranking function is can be used for what Maria presented there, but I don't have time to talk about that. So again, for every term, there is a unique canonical form. And this unique canonical form modulo some renaming bound variables of the lambda abstract. Also, this here, P1 to Pn, they're bound variables that can be renamed consistently with. So modulo renaming of these bound variables with lambda standard way, and modulo renaming the variables that are bound by assignments here. Everything goes very pleasantly until you figure out actually. So this goes. So here is about logging information. I don't have time to introduce the 10+ rules. Next week, I'll present examples with reference, and I'll include the reduction rules. Here, I included only one. So again, here we have with this recursion term, here we have this, oh, excuse me. So logging here is P1. You save information P1. The value of A1 is computed and saved, logged in the memory P1 or PI, and it is available for reuse. You don't need to prove something repeatedly. You prove something once, and there is actually parametric way to do that. I'll show with the example. And the proofs, they will refer only to the log. Other proofs, they will refer only to the memory where a parametric proof is recorded and it's logged. Specific instantiations can be obtained by this parametric proof. So I will show only here one rule just to demonstrate this chain rule. It's not necessary, but take a look. Do we need, take a look on the term 4a. So one reordering doesn't matter there. So the order is dependent on special ranking function. So if we have two assignments, in P we save the value of a term A, and in Q we save this lambda term. Well, this lambda term, lambda y, this y with the arrow, it's a vector, and P is applied to, in a correct way over a vector of variables. So this is actually the notation equivalent to P. So what we are doing, so here P already has locked the value of the term A, and then in Q, P grabs lambda y, P applied to y, actually grabs whatever was already in P and saves it in Q. So this is kind of, you don't need to log Q. We have to get rid of it. And here I get treated this way. Very carefully, of course. I replace all occurrences of Q with P. And so in this way, there is one drawback here, that the chain rule, it reduces the number of the assignments. But the canonical forms, if they are chain free, they still have to have two terms to be algorithmically equivalent. They still have to have the same number of those assignments. The vectors, they have to be the same, Maria. And there must be correspondence between the assignments with the notational equivalencies. So this is useful. And where do this repeated saving in Q and P appears from? One of the rules in the reduction calculus introduces a lot of such redundant, and we better get rid of it. But there is one place where, in the analysis of natural language, including the natural language of mathematician in mathematical text, where such information can be very useful. When two different components of a sentence, for example, you compute the value of one portion of the sentence, and you compute the value, the logic formula, the logic representation of another part of the same sentence, and you have to link them. Then this is important information that tells A was the value of the verbal phrase, Q comes from the value of the noun phrase, the subject noun phrase, and you put them together, and then you keep this information because it will maintain the linking, logging, the log of the information of the noun phrase, the subject noun phrase, and the value of the verbal phrase. So it depends, it's strictly not necessary, this rule, but it can be used. So now I go to a baby example. So here, the bluting parameter pattern of an algorithm. N divided by D, and N is A1 plus A2, and A1 and A2 can be any arithmetic expression. Here I took very simple expressions that look like constants, right? In A1 is saved the value of the constant 200, 200, A2 is 40, and D is 6. So now these are constants, and you think that there is no algorithm there. Well, think about the number system, the base of the number system. Is it 10? Is it 16? 12? So the values of 200, the natural number 2, and this is just a name, a constant. And this constant, the value, the natural number, it depends on the number system. There is an algorithm there. The standard example in the programming language is pi, the number pi. You don't reuse again and again pi. You declare it at the beginning, calculate the value, save it in a location P, and reuse P rather than the location, the declaration of the way the value is saved, rather than computing it again and again through the algorithm. So here is even with numbers. So now, if we are in base 10, all these three terms, A1, B1, and C, they have the same value, 20 something. So they have the same denotation, and this denotation is computed in different ways, right? The three terms, they represent three different algorithms for calculating the same denotation. And here in C, there is something very important. You don't repeat A1 and A2. They can be, A1 is 120, A2 can be again 120. You don't need to compute it twice. So there is a theorem that tells that there are canonical forms, terms in canonical forms that cannot be represented by any lambda term. And this is a criteria if you have at least two occurrences of a memory variable, two different occurrences in two different parts, then there is no lambda term for computing that. I'll show next week more examples. But so now, well, how do we put the restriction there that D must be different from 0? If D is equal to 0, then the value of these terms, all of them, is error. But we have to, is erroneous. There is no value there. It's partial function. But here in the domain, we introduce what was today star. Here we call it error. So how do we introduce this? By those terms such that. So here is the restrictor term R in A2. So N divided by T, D, this is a term, subterm. And this term is subject to restriction. And this restriction contains two predicate formulae, and actually three. N is a natural number, D is a natural number, and D must be different from 0. So these are actually can be represented by conjunction. And there is a very important reason why I don't use the conjunction, because of the, here the important thing for conjunctions is because the commutativity. And they're commutative, but here the order of the conjuncts, how they're computed, depends on a ranking function, not permute all of them. So that's why it's better to keep them separately as a list, and the list can be ordered depending on a ranking function. So this, if you have questions here with this baby. So now this 8B can be released, and we get algorithm, parametric algorithm. And this A1, A2, and D in A2, they can be very, very complex expressions, very, very complex terms, not just these constants, the same everywhere. This is a specific example of specific instantiations of these two memory location. This is what we put there, but it can be anything, any complex term. So here is another, again, example, this example about cubes, the language of the blocks. There is a open proof prover and verifier from Stanford for education. And there are a lot of examples there. It's extraordinarily useful software. So here I use to express that the cube, what was this? The cube is large. With this simple example, there are several things that I can talk about. So first of all, in first order logic, the definite descriptors, they are usually translated in a Russellian way. There is exactly one object that has that and that property. When we say the cube is large, do we say that there exists exactly one object? No, that's a consequence. And if you have a proof system, you can introduce such as a meaning postulate that from this sentence, the cube is large, you translate it into a formula. Here is one formula. And then you can introduce special meaning postulates, and you can say that the existence, the uniqueness, is a consequence. So here, on the left-hand side, on the left-hand side of the render operator is a natural language. This mathematical text is full with such determiners. The number, the function, etc., etc. And then it has, in order to get a noun phrase, a quantifier. So actually, in Russellian way, is a quantifier. Here is not a quantifier. The type is E to T to E. E to T is the type of the properties of individuals. So E to T will be contributed by the nominal that follows the determiner D. In this case, cube. So cube is a property of entities. It will be true for those entities that are really cubes, and it will be false for objects that are not cube, and thereby the objects when the robot cannot identify them, and then it will be a known value. That is also possible, but it can be erroneous. If the robot points to a table, of course, it's not a geometric object, so it will be error. So here, C, I have instantiated with this property. So cube is a constant. You can assume it's a constant. And this constant is of type E to T, which means a constant that designates properties of individuals. And it gets combined, the and cube gets combined together, and you get 11b, 11c. This is one term. So here, the typical translation is you apply D, the value, the logical form of D. You use the application term, and you apply it to cube, and then you can use the reduction calculus to reduce it to its canonical form. Here, there is a trick. Compositionally, I don't need to have a recursive term and to reduce it to its canonical form. I just combine the canonical form of D, it is 12a, and the canonical form of C, which is cube, and then I get the canonical form of the expression the cube. Then is large. So here is large. I translate, this is a verb phrase on the left-hand side of the render. It's a verbal phrase. Its mathematical text is full with such sentences. Any sentence, it has to have a verbal phrase, and we need to translate it into a predicate. So the verbal phrase expresses a predicate that applies to the object designated to the subject noun phrase. So here is large is translated very simple. You can directly translate it as a constant is large, but I prefer here to translate into D, and D is a memory location. It's a recursion variable. And then I put inside the B the value of the constant is large, because actually we can replace is large with is small, is bigger than another, because the verbal phrase can be more complicated than it can be a word followed by its complements. So I prefer this because we have simple algorithms, but they are still algorithms. And then the sentence, the cube is large, is directly rendered into the canonical form of the application of the term T to the term T0 above. But rather than decomposing using the reduction calculus, I directly get the 13 the canonical form. And the canonical form, 13, has this chain rule. You see, in E, we save I. And I is the value of the D applied to C. And D, in this particular case, I put the value of the determiner the, but it can be the determiner every cube rather than the, or exists cube, etc., etc. 3 cubes are large. So that's why here, again, the chain rule keeps memory of what was combined with what. So one may prefer to keep, it looks like redundant assignments, but it keeps memory of how many times compositionally sub-expressions has been combined. So, but with the chain rule, here is what we get. So 14a is without the chain rule, 14b is after the application of the chain rule. So we lose them with 14b, we lose what was combined with what compositionally. So now there is another thing that I want to say here about this is large. Yeah. So in the natural language, is it the same to say a large elephant and a large fly? The same here. The predicate is large depends, it's a context-dependent predicate. Do we apply it to a number? Large numbers, cardinals, ordinals. Or do we apply it to geometric objects, cubes? So is large for the geometric objects, it depends on the context. In the context, we may calculate the volume of a geometric object, and above certain threshold, those geometric objects are large. Between some border, they're medium, and small below some threshold. And this is context dependent. So actually, is large, next week I'll show example, it depends on cube. Is large is a predicate that doesn't apply on individuals, but it applies on properties. So is large has to be applied over cube, and we'll get large cube as a predicate, or large number as a predicate. So large is a dependent predicate, and the arguments are not objects, but properties. And the values there, they depend, context depend. So the denotation of is large should depend on the context. So I think I have introduced the very basic, just the glimpse. But there is a lot of work, so one needs to define the reduction calculus, and the reduction calculus has to be carefully defined. Let me go back here. I don't think I have put here, or maybe I have, yes. So here, there is a criteria for acyclicity. And I didn't include it because I didn't know that I had enough time, but there is a criterion. So if there is a, for each such recursive term, one can define a ranking function, and the rank, and this actually is related to the previous talk of Marie. So rank is a function from AI to AJ, and then the rank of A is going to be lesser or equal to J if I occurs, if PI occurs in AJ. So the rank of P of I will be lesser, strongly lesser than the rank of AJ, PJ, because PI and PJ are named memory locations. If P and I belongs to the free variable of AJ. So it's a wonderful criteria for acyclicity. And if one keeps the acyclicity constraint, imposes on 3b, then you can easily prove that the language the formal language, the well-formed terms, they're all acyclic. And as soon as this acyclicity constraint is dropped out, one gets full recursion, which you align. So now allow the cyclicity, the cyclic algorithms. So there is one thing, so the reduction calculus has to be defined very careful for all of these operators, including for such that, and the scoping here for the intentional expressions, for knowledge, beliefs, statements, etc. The domains of the statement, one has to define those reduction rules very carefully to maintain the cyclicity, not to drop out of that. It's very nice. I think that Moschovakis figured it out. So this is what I wanted to tell you, just to give you a glimpse. There is also another thing. There are terms that have no algorithms for computing their values. They're algorithmically without any meaning. You get their denotations directly. So the canonical forms, if we go back to that, if this recursion term is the canonical form 3b, is A1 to AN, then they are explicit without any occurrences, this binding operator weight them. They're explicit and irreducible. As long as you decompose the term, you don't want, you can rename bounding variables with the lambda terms, etc. You don't, some people they tell, well, can't we replace P1 and Pn in A0? Not algorithmically, denotation yes. So this is the Lat expression. If you stay in the denotational, you can, the denotational function, the denotation of this term is actually defined in that way. You take the denotation of AI and you use it to compute the denotation of A0 and according to the ranking function recursively. But that's for the denotation. The algorithm for computing this term is this system of equations. And there is a guarantee that by recursion theorems, the first and second recursion theorem, that the fixed minimal point is the solution of this, what is inside of P1 to Pn. So it's a mutually recursive system of equations. And there is one thing here. One can go above the well-founded sets. So the domain, the semantic domain of the entities, including the numbers, it can go above the proper sets. It can go into proper classes. That is fine. Then you be interested in the maximal fixed point of such equations. The minimal fixed point is about the recursion. When you stay in the universe of the sets, if you are interested in classes, you go into maximal fixed point. I think this is what I wanted to present today, just a glimpse on the entire system. So inside of the formal language, again, there is a syntax of these two versions for acyclic recursion and full recursion. Then the denotational semantics follows the term structure. The algorithms are determined by the canonical forms. Canonical forms is irreducible, and this is. So beta reduction applies denotationally. Lambda terms, you don't algorithmically use beta reduction. In certain simple cases, I somewhere investigated where, but algorithmically no beta. You keep the things decomposed. And there are terms that if you apply beta, then you'll nest them inside and you wrongly compute pi several times or cube several times. So this is it.
Очень.
maybe just to, I'm sorry that Maria didn't include such. There is a criteria when two terms represent the same algorithm, which means that you will have two different vectors there. One is for A1, A2, and N, and another one for B1, B2, Bn, and the head in one term is A0 and the other one is B0. And one needs to find correspondence between AI and BI. And this means that the vectors have to be reordered so that AI is the notational equivalent to BI, and then they're algorithmically equivalent.
But the computational equivalence of two algorithms is, of course, undecidable, right?
So here, this is open question. I haven't arrived, I just tried to. So here, that's again, probably something. So whether two terms are algorithmically equivalent, it depends on whether you are interested in the, it is the stand, I think Tait from the lambda calculus, he proved the decidability. So when it is about a specific universe, specific domain, it's one thing.
If you have a finite domain, okay.
Yes.
But if you have an infinite domain.
Yes, if you are for any domains, as soon as you quantify over all domains, it's an open question.
Yeah.
And the reason is when you are in specific domain, the reason is that if you have even finite number of constants, they can be interpreted. The interpretation function decide is the value, and then they can be interpreted who knows how.
If you have a finite universe, of course. But isn't your calculus Turing complete?
I don't know yet. It's open question.
Okay.
Because I introduced this such that
but
the
you
scope
have recursion and you have.
Yes, yeah, it's still open. One has to. One has to work there.
Okay. Yeah.
And then the algorithmic equivalence that I mentioned matters. So one introduces as axioms the denotational equivalences, simple denotational equivalence of explicit irreducible terms, the most basic ones. There, the denotations are easily, but you don't know how many, because you don't know when you have constants. The constants are the thing, because they have, so for natural language, I think that applies for the natural language of mathematics. In the natural language, how many arguments we have? I think 3. 3, not more than 4. I think with efforts one can find.
Imagine the number 5 plus or minus 2, or was it 7 plus or minus 2?
One thing that introduces, and very important actually, and I introduced it in situation theory. Here, in all these terms, in logic, we skip the time and we skip the space, and these are very important. So those, they go quietly in the language, even in the mathematical text. It depends whether certain object is a cube and it went through some disturbances, it became, somebody converted it into a sphere or dodecahedron. So this is time dependency that is missing in all these predicates. So then +1, or if you encode both the space and the location and the time, they can be encoded, the pairs, they can be encoded by Montague. He used that for the possible worlds. But you can skip them separately. In artificial intelligence, which means improvers, when you apply logic and provers for artificial intelligence, you have to be very careful to include the space and the time, because the robot has to know the time when the robot has to go somewhere and do somewhere, and the location. So there, those predicates, they have 1 extra or 2 extra arguments for time and for space.
Okay, so I suggest that we go to the coffee break and continue the discussion during the coffee break. Can you stop the recording? And because we have taken 10 minutes